So that's why this field, which is this one, this is called as a transverse electric field. And it is only formed if the charge is an accelerating charge. What should happen to this field pattern if I, let's say, want to observe the field at even a later time, t0 plus 2 delta t? What would happen to this field pattern? Because the new field would have propagated further, so this, the blue arrows, they would move twice more distance in the meantime, so you would have something like they would then be on a circle of twice the radius as the previous one. And they would keep on moving out. So on this side, they would keep on moving out along this direction, which is and in this direction, they would keep on moving in that direction. And you don't have any field components of the blue, of the transverse field along this direction and along that direction. So the field direction you have are here, so these would move in that direction, these would move in this direction. So they would, so this is kind of a circular field which expands in time. And it expands in time with the speed of light. So yes? Because what happened that the charge was initially stationary and then you suddenly give it an acceleration in this direction. Because of this acceleration, downward motion, a new field was created, and that field, the field basically changed, so the new field has to propagate. And the new field, or whatever field is, it always propagates with the speed of light. So if there is a discontinuity in the electric field, it would also propagate with the speed of light. So what does it tell you? That an accelerating charge produces a transverse electric field, and that transverse electric field is called as the radiation field, or the radiation electric field, so to say. So we would call this as E radiation, which propagate out at the speed of light. Okay, what would happen afterward? Let's say at a later time when there is no acceleration at all. So this guy is moving with a certain velocity, constant velocity v. What would happen to the field then? So let's say if this charge Q then is moving with a constant velocity v, so there is no acceleration, then the field which goes out of it, it won't produce any kinks. You would have this pattern of the electric field, and this electric field would move with the charge as it is. You won't have any discontinuity formed. Discontinuity like that, by discontinuity I mean that kink, it only forms whenever you have a change in motion. When the motion doesn't change, you don't have that kink formed. So that's an important point to note, that you should have accelerating charges and not just moving charges. So let's try to find out what would be the magnitude of this. So if you have, let's say, an accelerating charge which is plus q and which accelerates in this direction, and you want to find the electric field at a certain location r, and the electric field we are interested now is the radiation electric field or the radiated electric field. So that's the circle I draw. So what if I want to find the electric field, the radiating electric field at this point P, which is given by the position vector r? What should be its direction? It is perpendicular to r, and as we found out, this radiation field will be in that direction. So let's form two components of this acceleration. So let's say acceleration would have a component. So if I draw a normal here, so you would have one component of the acceleration which would be parallel to the r vector, and you would have another component of the acceleration which would be perpendicular to the r vector, which is the position vector. So what is the relationship between this acceleration vector and the radiative field vector? They are oppositely directed. So what you can say is that the radiative electric field vector, this should be opposite to the component of the acceleration which is perpendicular to the position vector r. You do it for any point, you would get the same thing. For example, what if I have that point at this location, so that this is my r vector now. What would be the electric field here? Upward. That would be the E radiant direction. What would be the component of the acceleration which is perpendicular to this r? The whole acceleration is perpendicular to r now. So what you have in this case is this A is basically for this r, this is your A perpendicular. So what does it tell you? That you have a larger perpendicular component of the acceleration here and a smaller perpendicular component of the acceleration here. So if you have a smaller component of the acceleration, the electric field would be small, but if you have a larger component of the acceleration which is perpendicular to r, the field would be strong. So that's why you have this proportionality here. You not only have the electric field direction oppositely directed to the acceleration, but it's also proportional to it, which means that if the magnitude of this component increases, the magnitude of electric field changes. That's why you have stronger fields here and weaker fields here. Okay, at these points, or maybe just, so what would be, let's take a point here. So my r vector, so the third r vector I have is this r vector. What is the component of acceleration which is perpendicular to r now? It's 0, because all of this acceleration is along this r, so it means that in this case the perpendicular component of A is 0, and that's why you don't have any radiative electric field there. Same would be true along the opposite direction. But this is not the only thing which it depends on. It also depends on the quantity of charge you are moving. If you are accelerating a bigger charge, the field which will be created here would be a bigger field, and the field, if you have a smaller charge, the field which you would create would be a smaller charge. So you also have a proportionality with the charge itself which you move. I mean, it makes sense. Charge agar hoega, so that would be. The larger it is, the larger. What else should it depend on? The distance, of course. So the farther you are from the charge, the smaller should be this electric field. So it depends on the distance, and that distance is the magnitude of R. And I won't give you all of the calculation, but what I would tell you that the power on this R is equal to 1. It's not R squared, it's just R to the power 1. That's why the difference between the Coulomb field and the radiative field comes from. So what would be the electric field? Just the normal Coulomb electric field. It should be proportional to the charge divided by R to the power 2 and not R to the power 1. And it has important consequence for this. Of course, this Coulomb field, it doesn't depend on the electric field as well. So this would be the field produced by this configuration, for example. Yes? Yes. No, it's not non-Coulombic, it's radiative electric field, yes. Yeah. It's moving, yeah. It's not moving, but it's moving radially outward, but it's directed tangentially at each location. So there's a difference between that. So let's try to, so I won't give you the full calculation because it's quite involved, but what I would give you is the full expression for the radiative electric field, and this is given by 1/4 pi epsilon naught minus charge multiplied by the component of the acceleration, which is perpendicular to R, divided by R to the power 1, that is multiplied by C. C squared rather, sorry. Yeah. That's a constant again, because C is the speed of light. So, if you compare it with the Coulomb, normal Coulomb electric field due to a charge, that would be divided by R squared, and that would be directed outward. This is directed negative to the component, negative to the A perpendicular. This is directed radially outward. So these are the two fields. How do they vary with space? How do their strengths vary with distance? So the magnitude of the Coulomb field, which is this one, it drops off like 1/R squared. So if you draw it, what you would see is it would be something like this. It drops off like 1/R squared. And this is the normal Coulomb electric field. What about the radiative electric field magnitude? It drops like 1/R. This would be 1/R. So that the radiative field magnitude. So 1/R square, it drops off rapidly, 1/R drops off slowly. So what should you expect at very large distances? So let's say I have this accelerating charge and I'm looking at this location far from this here. Which field should have stronger contribution? The radiative field, because this radially outward field, which is, so from the field lines you can immediately see at the density of field lines of this Coulomb field, it rapidly drops. So यहाँ पे density ज़्यादा है, you go out, the density rapidly increase. But if you would look, so if I look here, you have one line here, you have another line here, and next line going somewhere. So those lines are very far apart. So the Coulomb field here is a very weak field. But what would you observe? That if you look at this radiative field, it would drop it would, if you look at that radiated field, it would have propagated until that location. It might not drop by that much. It would still have some considerable component. So it drops very slowly, the other one drops off very. So that's why you see light from the stars. Because what are stars? You have oscillating charges there which produces electromagnetic field, and they propagate and propagate, and those fields are radiative fields and they move out. But when they reach Earth, even if you take R very large, it won't really go to zero. You would still have some non-zero value of the electric field magnitude. That's why you see the starlight even at such large distances at the astronomical scale. Just because of this reason that you have R to the power 1 here. Okay, so, but what we saw there is that let's say if there is, so this acceleration was for a very short duration of time, and when that acceleration occurred, this emitted or this released some transverse electric field which was this E. So let's say acceleration was for a short duration of time, and during that short duration of time it emitted some of those radiative fields, and afterward there was no acceleration, so there would be no emission or there no propagation of electromagnetic. This radiative field, so you would have a small packet of electric field which would be coming out of this one, which would be the radiative electric field on this side and on this side, and they would propagate outward. Similarly, you would have here as well, with a smaller magnitude, and so on. Even if the charge stopped moving, it would keep on propagating, because that kink has been released from the charge, and if that kink has been released, it's no longer dependent on the charge, it would keep on moving. Okay? So, but of course it would be not close to it, it would go far and far, so you won't see it closer to this. So, would such an electric field would exist on its own? So if we look at this case, we say that this condition is only possible that if you have, in a region you have electric field, but you should also have a magnetic field which should be perpendicular to B, and such that the direction is such a way that the E cross B gives you the propagation direction. So it means that this electric field should also have a magnetic field as well. Otherwise you won't, so this configuration, for example, is not possible. It won't obey the Maxwell's equation. If you have just this thing, or if you have just this magnetic field, it's not possible. If you try to solve Maxwell's equation for that, that gives you nonsense values. So what it means that this field should also have an electric field, magnetic field, and which should be the direction of that magnetic field. So it is given by the direction of the velocity. So if let's say this is the propagation direction, so the magnetic field direction here should be such that the E cross B would give you the direction of that velocity. So what would be that thing? So it would be E cross B. So if I have E in this direction and B outward, then I would get this direction. So I can write that the B field in this location is out of the ball. And both E and B, which are lumped together, they move out, they propagate out in either direction. You would have this case here as well, and here as well. Let's solve this. Okay, let me ask another question then. So, you accelerated this for a short duration of time, and then it start, and during that acceleration it emitted those radiative fields. Then let's say it is moving with constant velocity. If I slow it down suddenly, then what should happen? You would emit another electromagnetic field, but that field, radiative field, it would be in opposite direction because you are slowing it down. So acceleration आपकी किस direction है? उलट है. So the field would invert. So what I would do next is to generalize this thing and solve for a case so let's say this is a free space given by x, y and z direction. Yes? It is so E, this direction will be here, okay? So E cross B should give you the velocity direction. That's true. It should be out of. That's true. So E cross B, it should give you that. That's true. Similarly, it would be cross there as well. Thank you. Yeah. So let's say I have a charge plus Q again. Imagine it's a positive charge. But now I'm taking a more general case such that a force is applied on it in such a way that it is oscillating that charge. So you can have acceleration on either direction now, but it is an acceleration which is a sinusoidal acceleration. So that's what you see in most of the cases. Let's say the charge is, so this charge Q is displaced on either side by a plus, from plus Z naught to minus Z naught with a certain frequency. So what should be the position Z of the charge as a function of time? That would be given by Z naught into, let's say if you started from this location, then it is given by omega t, where omega is the frequency with which you are oscillating that charge. So remember, this omega is 2 pi into the frequency which you normally measure. So this is linear frequency, this is radial frequency. So the normal frequency which you represent in hertz. Okay? Let's say if you have an AC current is 60 hertz. This 60 hertz is this thing, this F. So omega would be 2 pi into 60 hertz. So that's something which you need to remember. The omega is not the linear frequency which you normally measure in your experiments or anywhere. Okay, so whatever the case may be, but let's say you have a force which is oscillating force, and that oscillating force, it oscillates the charge by in such a sinusoidal way. What should be the velocity along Z? This would be given by dz by dt, and I have to take its derivative, so that would be equal to Z naught omega sine derivative is cos omega t. That would be the velocity. It would be also an oscillating function. What about acceleration along Z? That would be equal to the second derivative with respect to Z. So that would be equal to minus Z naught omega squared, again sine omega t. True. So that's the oscillation back and forth between these 2 points, so along the z-axis. And then I want to find the radiative field at a certain point P along the y-axis. So the oscillation is along z-axis, but the magnetic field is, I want to find the radiative electric field at this location P, which is along y-axis. Okay? So what should be the direction of this electric field I expect? Your radiative electric field है किस एक्सिस के along होना चाहिए? What do you think? तो यहाँ पे acceleration किस एक्सिस के along थी? इस वर्टिकल एक्सिस की जो फील्ड यहाँ पे क्रिएट हुआ था परपेंडिकुलर टू दैट वो उसी एक्सिस पे हुआ था. द ओनली थिंग वाज कि एक्सेलरेशन इस डायरेक्शन में थी, द फील्ड वाज इन अपोजिट डायरेक्शन. बट सो if you have an acceleration like this, you might have a field which would be, the radiative field would be either up or down dependent on acceleration, up or down. True? So let's say that's the case. So what should be the that radiative electric field? It would be, or the magnitude of that radiative electric field. Let's say if I want to find its z component, which is that component along z. So that would be given by 1 over 4 by epsilon naught minus charge multiplied by a perpendicular divided by r. That would be then multiplied by c squared. So 1 over 4 by epsilon naught minus q. So that's your r vector now. And you have to find the acceleration which is perpendicular to r, because इस expression के अंदर आपके पास electric field का perpendicular component है. And what is that component? It would be the z component of the acceleration, which you already have here. So that would be minus q into the z component. It would be minus z naught omega squared sine omega t divided by c squared r squared, where these are the distances. So I can rewrite the whole thing as radiative field z component. This is given by charge by 4 by epsilon naught into z naught into omega squared multiplied by sine omega t. So this thing I can write as E naught into sine omega t. So this is all a constant. Z naught is constant, omega is constant, c is constant, epsilon naught is constant for this situation. So I have lumped all of this into E naught, and what I am left with is a sine omega t. Get it? R squared, R squared है, sorry. R, yes. Not R. That's also, R is constant as well, because I want to find the field at just this location, so R is constant. So what does it tell you? That this electric field would oscillate with a sine frequency, so with a sine function. So sometime at one point maybe this is up, at another point it would be down. So now to generalize it, what I can say is at some location you would have the electric field up, at other location you would have the electric field down. I won't draw the two vectors on the same location, but this is how this field would. So at some locations it would be up, some location it would be down. So it would sinusoidally vary the electric field as you go along. So what should be the direction of the B field then? Because it would propagate out in this direction. So that's your velocity direction. So for this case, the B field should be along the x-axis. So you have E cross this should be. So the B field would be along the x-axis. What would happen to this one? So you would have E in this direction, you would have a B field which is along the minus x direction, and in this case you would again have a B field which is in the minus x direction. And because it's a sinusoidal function, so this thing would gradually move from here to here. So if you draw this electric field, what you would see is you have a gradual change from a plus sign to a minus sign, because it's a sine function. That's what you will see. So let's try to draw this electric field at this location. So I would restrict myself at this location and see how does the electric field change with time. So I'm not moving around, I'm just sticking at this location, and I have some meter which gives me the electric field direction and the electric field strength, and I want to find out what is that. So let me draw that thing. So let's say this axis is time, this axis is x, and this axis is z. So how would the electric field change? It would change like this. So it's a sine function. So at time t equals to 0, it would be 0, but as it would move out, this electric field would increase in this direction, but then it would start decreasing because it's a sinusoidal function. So it's a sine function. So this would increase and then decrease. Then it would reverse direction because the negative cycle of the sine function would start and the electric field would reverse its direction like this. That's what this expression stands for. कि जो z component है electric field का it varies sinusoidally. So sine, there's a sine function, it would be 0 here and it would change like this. But as we found out there, we have a B field as well, and also the electric field magnitude and the magnetic field magnitude are tied together by this relation. So अगर E magnitude change होएगा, B magnitude भी change होएगा. B would be equal to E by C. So if E is small, B would be small, but दोनों की डायरेक्शन जो होगी वो आपके पास परपेंडिकुलर होगी. So let's say in this case अगर आपके पास इलेक्ट्रिक फील्ड अप है तो B की डायरेक्शन क्या होगी? आपके पास X की डायरेक्शन होगी. So let me that's your B field, how it varies with time, and that's your electric field, how it varies with time. This, remember this is the time axis. But you can also, so this charge is oscillating like this, and this such kind of a electromagnetic field is coming out of it. So you can also take a picture shot of that at a certain time, and you would see such a configuration again. So you can also say that this is how it looks like along y-axis. So you can solve for it, and what you would get is E radiation as a function of z. This is given by E naught sine kz. That's a function of z, where k is a certain constant which is given by 2 pi by lambda. This is something which I will introduce later. So you would have a sinusoid. So if either you are looking at a certain point, and with time, as the field passes through it, you would see that this sinusoidally varies. But if you have such a field which is going out, and if you take a picture shot of it, you would see that you have a wave-like function along this direction as well, and that's what. So you can write T here, you can write Y here. Both would be true. So how does this was produced? If I have a charge Q which is moving along, which is oscillating along z-axis. What if I have a charge which would oscillate along x-axis? You have a charge which oscillates along z-axis. What kind of a field would you produce in that case? So you would have electric field now in this direction. So what you would have is something like this. So now the electric field would be horizontal or along x-axis, and the magnetic field would be along that's your B field, that's your E field. So if you have a charge like oscillating like this, so the electric field it produces also oscillates like this. But if you have a charge that oscillates like this, the electric field also oscillates like that. Yeah. Sorry? Not Z, sorry, Y. Yeah. Because it propagates along Y, sorry. Yeah, that's good. It is? Okay, they have to be inverted. Yeah. Okay, I made it. Let me invert again. So you would have E cross E. So yeah, just E is होगा. It would still be along x-axis. So in this case it's plus axis, in this case it's minus axis, and B would be like this. Because E cross B should also always give you this propagation direction, which is B. So, yes? It can be on one point, it can be along a certain axis. Yes. So, as I said, it depends on how they carry. So, if you are looking at, if there's an oscillating charge and you are looking at this location, and you have a certain device which tells you the direction and magnitude of electric field, let's say if you have such a thing, then you would see that with time, this field would go up and down, up and down. So if you draw that electric field as a function of time, this is what you should see. And this is what you should see in terms of magnetic field. But let's say if you have this wave which is going out, and you are not looking at a certain location, but you have a wide view of angle and you take a picture shot of it, you would see that a wave which is along y-axis. So you can also put a y along that. So it depends on what you are seeing. Whether you are looking at a certain point, or whether you have a broad, a panoramic picture, and you take a shot of that. Depends on what you. It passes will travel. Time, okay, it won't change. If it is free space, so the question was like, if you have just one oscillation, you have to have one pulse which will go out, and it won't change with time as long as it is in free space. So, okay, you can have two informations here. So, okay, I would come to that point, but let me clarify another concept, which is the concept of polarization. So, if this wave stays like, so if this oscillation stays like this, and it is always oscillating along z-axis, so the resulting electric field you create, your transverse electric that would always oscillate along z-axis. So what we say in this case, so it can be along plus z-axis, it can be along minus z-axis, but it will always be in this along z-axis. So this plane which is formed by this electric field, this is called as plane of polarization of electromagnetic field. So electric field vector जो plane बनाती है, so which is given by basically ये वाली plane जो है, which is zy plane जो है आपके पास. Zy plane, this is your plane of polarization. So what we say that the electric field, this electromagnetic field is polarized along z-axis. But if you have such a field, this oscillation आपके पास क्या है along x-axis. So the electric field always oscillates along x-axis. This electromagnetic field is polarized along x-axis, not z-axis. So it depends on कि आपके पास oscillations किस direction में है. You can have a polarized. अगर वो different direction में है, you have a polarized wave. If let's say this charge which is oscillating, it oscillating randomly in all different directions. You would have oscillation in all directions, and this would be a non-polarized. So light oscillating, that would be a non-polarized light which comes out of it. So this is an important concept which you need to understand. So let's come. So if let's say this is time, and this is distance y along which it propagates, and I can draw my electric field either along with time, or I can draw my electric field along distance. I can do either of them. So if you take this point and if you take this point in the next oscillation, they are at the same situation. So they are both at. So if you take this time, which is let's say t1, and if you take this time, which is let's say t2, so the difference of those times, they would give you a time such that t, this is equal to t2 minus t1. And this is the time for one full oscillation, needed for one full oscillation of such a wave. This is called as the time period of this oscillation. Time period of this oscillation of electromagnetic field. This is the electric field magnitude I am plotting here. This thing, so this on this axis you have the electric field magnitude. So this magnitude, so the maximum magnitude it can attain, this is called as the amplitude of the wave. And in this expression, the amplitude is given by E naught. On this side you have, along this axis you have y, which is some distance, so this is second, this is some meter. So if you take those similar points, so this is given by y1, this is at y2, so this distance would be, this is called as the wavelength, which is lambda. So your linear frequency, it is defined in a way that this is given by 1 over t, which is towards the time scale. So this gives you the number of oscillations per unit time. And then omega, which is the radial frequency, this would be 2 pi into f, or this is equal to 2 pi by t. Similarly, if you take 2 pi by lambda, which is lambda is the distance of one wave, so it gives you a certain number which is called a k, and this is called as wave number. So this gives you the number of waves per unit length rather than per unit, sorry, lambda rather than. So these are the few configuration. This is frequency, which is the linear frequency. This is the angular frequency. This is the wave number, and so on. So that's how you characterize 2 pi, right? Or that would be. Okay, so you have something which is called as electromagnetic spectrum. What is an electromagnetic spectrum? Based on the frequency, so the unit of frequency is hertz. Based on the frequency, you can classify electromagnetic field. which frequency range is you have. So starting from very low frequency like radio waves, then you have microwaves, then you have infrared, you have visible, then you have UV, then you have X-rays, and then you have gamma rays. So this is in terms of increasing frequency. You have different ranges of frequencies, and because of different ranges of frequencies, you have electromagnetic field. So what it would mean, such a wave would be produced by a charge which is oscillating slowly, but this a wave which would be produced in this electromagnetic spectrum would be produced by a charge which is oscillating rapidly, and as you go along this axis, the oscillation becomes faster and faster. So what our eyes can see is a very narrow frequency range which is in the visible frequency range. You can also classify as a function of frequency, but you can also classify it as a function of lambda. So this range in terms of lambda is from 400 nanometer to 700 nanometer. That's the blue and that's the red. So, and no matter what wave you take out of this electromagnetic spectrum, whether it's the wave which is detected by your radio, or whether it's the wave which is emitted out by a light, all of them would have the same character. They would have an electric field which would be changing with time, and they would have a magnetic field which would be perpendicular to their electric field which would be changing with time. And the direction of those two fields would be in such a way that they propagate in a direction perpendicular to both the electric field and the magnetic field. And they would propagate, all of them would propagate with the same speed, that is the speed of light. So, whether you have a radio signal, it would propagate with the speed of light. Whether you have a torch, it would propagate with the speed of light. This is your light will be. So, in all cases, whatever the electromagnetic field you have, it would propagate with the speed of light. Because that's what Maxwell equations give you. And Maxwell equation doesn't lie. So let's generalize it a bit further. You have, what we take is that you have a charge which oscillates. How do you normally achieve such a situation in real life? So there are different ways of achieving an oscillating charge. And I would give you a couple of examples, because you need oscillating charge to create electromagnetic radiation. Otherwise, you won't have this transverse electromagnetic radiation. So, if you have two metal rods like this, and you connect those metal rods with a certain sinusoidal source. What is such a configuration called? It's called an antenna. So what you have is, for half cycle, you would have this as positive and this as negative. For the other half cycle, you would have this as negative and this as positive. So what does happen? So in one cycle, the electrons are accelerated in one direction. In the other cycle, the electrons are accelerated in the other direction. So what you have here is such a sort of oscillating charges. So if you have this cycle of the AC source, then it would apply a force. So you might have positive charge here, negative charge here, which means that the electron would be, there we go. Okay, the electrons are pushed in this direction, and this side would have a positive charge on them. If you have the negative cycle, the electrons are pushed on that cycle, that part of the metal, and this side will get a positive charge. So you have charges which are accelerated in either side. So what you have is, you can create an electric field which would radiate out of this, and that field would radiate. Because the oscillation is in this direction, you would have a radiative field which would field radiate out in this direction. And the oscillation and the frequency of this field which comes out is given by the frequency of the source which you have here as your AC source. So that's one way of creating electromagnetic wave. The other one is, so that's something which is called as a dipolar antenna. That configuration is called as a dipolar antenna. Next you can consider, let's say, a bulb. So what does a bulb is? It is basically a high resistive element. You have a high resistance, you have current flowing, and you have a high resistive element. This current is constant, by the way, it can be constant. You have a high resistance. So what happens due to the high resistance? You have heating of the resistor, and the heating rate is given by I square R, which is the Joule heating rate. So if you have, so what happens in the bulb, in the normal incandescent bulb, is this resistive element, it heats up. And whenever atoms in the solids are heated up, they start oscillating violently, and the more you heat them up, the stronger they oscillate, and they oscillate with higher and higher frequency. So if they are heated up, they would oscillate with higher and higher frequency, the electrons inside a resistor, and they would start emitting those light, which is basically your electromagnetic radiation. And maybe you have seen different bulbs. Some bulbs are yellowish, some are whitish, some are bluish. So what's the difference between those bulbs? Basically resistance is different. So if the resistance is different, so the energy they get for oscillation is different. So the higher energy they get, the stronger would they oscillate, and the stronger, they would oscillate with a higher frequency, and they would emit a higher frequency as well. So if you have a red bulb, it would have the smaller frequency, it would have a smaller resistance. But if you have higher resistance, you create larger temperature, you get larger temperature, you have higher oscillating frequencies, and you might have a blue bulb. Of course, there are other tricks. People put shades on the bulb, so that's understood. If you just have, okay. Then this is not the only thing, oscillation. What happens inside an atom? So what happens if you excite an atom? So let's say if you have an electron which is in the ground state, you excite this electron and it comes here. It can also emit light. So it would emit light from moving from this high energy state to a low energy state, and it would emit electromagnetic radiation. Is there an oscillation in this case? There is an oscillation in this case, and that oscillation is the electric dipole oscillation because of between these two energy levels. That's something which you might study in high level physics. So what do you have is, for example, you have an atom. If the electron is here, it has a certain dipole moment. If the electron is here, it has a different dipole moment. And when this transition is to occur, there is a small oscillation between those dipole moments. And because of that oscillation, you have a wave packet which goes out. And after that wave packet it goes out, the electrons, it is in the lower state. So you do have oscillations whenever you have, by oscillation I mean acceleration. So I think I would stop it here because there is some, so you have to fill a certain form. So please kindly do it. Any question here?